In this lesson, we are going to put more emphasis on graphs, and we'll also just talk about advantages of AC over DC. In the exam guideline, it is said that we must teach you about the advantages. So welcome to the second lesson of electrodynamics. We're going to talk about electrodynamics graphs. Then we touch on the advantages of AC over DC. In the previous lesson, we spoke about AC, which is the alternate current, and we spoke about DC, which is the direct current. So, in this lesson, I'm going to put much more emphasis on two types of a graph. For AC, we're going to draw a graph of current plotted against the time and the voltage plotted against time. Even for the DC, we're going to talk about current plotted against time and voltage plotted over time. So, let us start from the graph of AC current. The first picture that we know about the AC is that we're going to have the negative values here. -1, -2, this is 0, this is 1, this is 2, 3, increasing to whatever value that we want. So because this one is alternating, we know that current is going to alternate in the negative and the positive because it is alternating. Then this one, because it's direct current, where current is moving in the same direction and continuously, so it means that if it is current, we're going to have a graph like this, and we represent that like this. Represent it like this. And you may be asking yourself, why is there an increase and a decrease? You can see that here it is increasing, and it reached its maximum point, it decreased. The same place, the same situation here. Here there's a decrease, then it reached this point, then it starts to increase. And it becomes 0. You can see that if this is current here, and this is current here, you can see that it gets to 0. It gets to 0 here, then it moves up about 0, then it is below 0. So that's what we need to explain from the graph. So these are the general pictures, the general ideas that we have. This is for alternating current AC, this is for direct current. It does not alternate between the positive and the negative in terms of representation. So now we are about to start to explain into details. Okay. The first thing that we need to know, which is very important, let us talk about the coil. I will draw a coil, like drawing a rectangular shape, and I can call it a coil so that you can understand. This is simply just a drawing. I want to make you understand something. You need to know that a coil is going to rotate and comes to different positions. If this is a coil is going to rotate like this. It rotates like this. So as it rotates like this, it is changing position. And you know, right as there is a rate of change in the magnetic flux, there's going to be an induction of EMF. We're going to have induced EMF. We're going to produce EMF as there's a rate of change. You can see that this coil is changing direction. It's changing position. So you'll find that at a particular time it is like this. It turns, it becomes like this, become like that, become like this. You can see it is changing position. It is in this position, it is in this position. I can say it becomes parallel, in a parallel position, perpendicular, parallel, perpendicular, parallel, perpendicular. You'll understand when I say parallel and perpendicular as I explain. Okay, let me just write my coil to be which direction. Let me make it to be in this direction. Yeah, so that you can understand. It is best I draw it in this direction, of which it is very difficult to draw this representation. That's why I'm holding this so that you can see it in 3D, or also in 4D, because as you get to learn, you get to know that we've got the X, Y axis and the Z axis. But that's a topic for another day. Okay. You need to know that in the coil there is a normal line. It all starts there. You need to know that in a coil there is a what? A normal line. There's a line which we call the normal line. This is the background information. This is what is going to make you understand. In the coil there is a what? A normal line. I'm going to write this normal line. It is situated in a way that when the coil is parallel to the magnetic field lines, then the normal line is perpendicular to the field lines. I hope you can still see that. What am I saying? In each and every coil, we have got a normal line. But the normal line is situated in a way that when the coil is perpendicular to the magnetic field lines, then the normal line is parallel. In other words, I'm saying that the normal line opposes the coil. Although the normal line is in the coil, but it is situated in a way that it opposes the coil. I think that's the best way to explain for you to understand. When the coil is parallel, look, we have got two magnets. We have got two magnets, north and south. Remember the magnetic field line? They are going to do what? To point the south, from north to south, as I gave you the analogy of colonizers when they came to our continent. They all moved from the north and east or wherever, coming to South Africa, which is Africa and situated in the south. So you can get to remember that everyone came to the south from all directions. So it is north to south. So these are a field line. So remember that here we have the what? We have the coil, which is rotating, and it is playing where there are electric field, which will represent by lines. So what do I mean? When the coil is parallel the magnetic field line, it means that the normal line is perpendicular. Let me put it like this. Let's say the normal line is like this. Let me just draw a line here. The normal line can be represented by this line. You see this line? When, although it will be difficult to demonstrate, but you will understand through saying words. When the coil is parallel to the electric field lines, you can see, right? When it is parallel, the electric field lines are pointing in this direction. Even this coil is lying, and this part, I can say, has pointed this direction. You can see, right? So what will happen? It means that when the coil is parallel to the electric field line, there is an angle between the electric field line and the normal line. Okay? Rather, let me erase this part so that you can see. Because this is the main important thing. If you understand this, then you have understood everything that I want to explain. You have understood everything. Okay, look at this. You remember that when we calculate magnetic flux is given by the area, the cos theta. Magnetic flux is given like that. When you remember what you were taught in grade 11, you know that magnetic flux is given by BA cos theta, whereby this B represents magnetic field. Then A is the area or area of the loop. Then theta is the angle between magnetic field. Angle between magnetic field and the normal line of the loop or the coil. I'll call it a coil. So we'll be focusing much on this theta. Theta is the angle between the normal line and the what? And the angle between the normal line and the magnetic field. That's what theta is. So this angle theta is the one which has got the main impact. Okay. So let me explain what will happen. I was saying that we have two magnets. We have two magnets north. We have got another magnet south. then we know that the electric field are going to move from north to south. If the loop, the coil, is parallel to the magnetic field line, it means that the normal line is perpendicular to the magnetic field line. Listen to this. Don't try to understand it. Just listen and follow it along, like when you are reading a cookbook. Listen. Don't try to think a lot of things about it. Just listen. I'm saying that the normal line is situated in a coil in a manner that when the coil is parallel to the magnetic field line, the normal line is perpendicular to the magnetic field line. When the loop is perpendicular to the magnetic field line, the normal line is parallel to the magnetic field line. That's the main statement. The normal line inside the loop, inside the coil, it is situated in a manner that when the coil is parallel, loop is perpendicular. It's like the loop, the normal line is opposing the direction in which the loop is lying. The loop or the coil in this state. We're talking about the coil. I hope you are understanding. A normal line is a line which is found in the coil, but it is situated in a manner that when the coil is parallel to the magnetic field line, the normal line is perpendicular. When the coil becomes perpendicular to the magnetic field line, the loop is parallel. I hope you understand. So, I was telling you that this loop is going to rotate. Look at it. Now, this loop is what? Is parallel. Look at this line. When the loop is parallel to the magnetic field line, the normal line is what? Is perpendicular. You can see that if you check this magnetic field line, they are what? They are perpendicular. Isn't it? They are facing this direction. So the angle between the normal line, this line, and this marker, it is going to be 90 degrees. And we know that cos 90 becomes what? Cos 90 is equals to 0, right? Which will make us to have a magnetic flux of 0. I'm going to explain that because when you draw the graph of this AC and DC, the position of the loop in the question that you are given is very important. So what am I saying? I'm repeating the same thing again and again so that you can understand. Look at the normal line. This is the normal line. This is the loop. The loop now is parallel to the what? To the magnetic field. And remember that this angle theta is the angle between the magnetic field and the normal line. Remember that theta is the angle between the magnetic field and the normal line. So when the normal line, when the magnetic field, as it is parallel to the loop, and the loop is parallel to the magnetic field, it means that the normal line is perpendicular to the magnetic field. It means the angle between the magnetic field and the normal line is 0. So look what will happen. Isn't it? This is the position at which the coil have turned. Look at what will happen. Then the coil turns and it becomes perpendicular to the magnetic field. You can see that the coil and the magnetic field lines, they are what? They are perpendicular. You can see that, isn't it? This is a magnetic field. If you can check the angle that is here, it's 90 degrees. It's 90 degrees. What is happening between the normal line and the magnetic field? Can you see? They are parallel to each other. So what is the angle between this line? You can see all of them that are facing this direction. The line of the normal line. What is the angle between them? It is 0. There is no angle between these two lines because they are parallel. You can see that this line is at the top of these lines of magnetic field. So it means it is 0. And remember, cos 0 will give us 1. Cos 0 will give us 1. Meaning that we are going to get a maximum number. So everything starts there. Then I'll come and explain current and voltage of everything. But what you need to be conscious about is that the normal line in the coil is positioned in the manner that when the coil is parallel to the magnetic field, the normal line is perpendicular. When the coil becomes perpendicular to the magnetic field, the normal line is parallel. You can see that. Then, if you got that, you can be able to draw a graph for current and time and the voltage and time based on that, because the position of the lobe, it is the one which is going to give you ability to be able to know where to start, to be able to know whether we have an EMF which is 0 or an EMF which is 10, for example. So I'm going to demonstrate this graph starting from there. I repeat, normal line of the loop of the coil is situated in a manner that when the coil is parallel to the magnetic field line, remember this is not, this is how. The magnetic field line, that in which direction? They are facing this direction, the magnetic field line, and this. So when the coil is parallel to the magnetic field line, you can see all of them. This is a coil. When they are parallel, it means the normal line of the coil of the loop, it is perpendicular. But when the coil turns and becomes perpendicular to the magnetic field line, can you see the normal line? The normal line becomes parallel. And that the angle becomes 0. So these graphs are going to be based on the position of the what? The position of the loop. The position is very important. Okay, let me demonstrate using a graph. On the screen, I'm going to display different positions, and from those positions, that's where we are going to start to draw our graph for current. Thing to demonstrate that this is the coil and this black line is the normal line, meaning that the normal line is positioned in the manner in which when the coil is parallel to the magnetic field, the normal line is perpendicular to the magnetic field. When the coil is perpendicular to the magnetic field, the normal line is parallel to the magnetic field. Again, when the coil is parallel to the magnetic field, the normal line is perpendicular to the magnetic field. When the coil is perpendicular to the magnetic field lines, the normal line is parallel. So there's going to be that change. As the coil change, it starts from this position. Then we know that the line, the magnetic field is parallel with the normal line of the coil. And that comes from when we were calculating magnetic flux, which is given by BA cos theta of everything. So, we're not interested in the derivative of anything, but what we need to understand is that for current, our formula is still going to remain being cos theta. For current, we use cos theta. Let me not talk about this thing of derivative because I will confuse you. Let me leave that out. I'll just tell you because this is the product of the derivative. For current, we're going to use cos theta. What do I mean by we use cos theta? Just like in this formula, whereby we have BA cos theta. Cos theta, for example, isn't it this is the magnetic field? This is the area. This is the angle between the magnetic field lines and the normal of the coil. So let's say we want to calculate the current. We want to calculate this formula is the formula which is I wrote at the top. I wanted to do the derivatives, but it is useless for us to make derivatives. It is not examinable for a level. I will just tell you the product of the derivative. I will just give you the formula as they are without driving them. So for current, as I was saying, current we're going to have cos as it is. Whenever we have a graph for current, let's say it's an AC. For AC we know it is going to alternate. Then here we're going to have a particular values. Let me have, I can't write numbers. Because if I write numbers, I'll be implying something. So I know here there's 1, 2, 3, 4 going up and -1, -2 going down, and this is 0. I can't write numbers because even here I won't write numbers. I will just tell you that for current, and here is the change in time. So let's say the coin is at this position, because the position which the coin is when you draw it is very important. Let's say the coin is at this position. When the coin is at this position, the coin is parallel to the magnetic field line. Let me represent that thing here. I'm having two magnets. North this side and south this side. Then here are the magnetic field line. Then we know that there is a coin between the magnet. Here is the coin. Let's say this thing is inside the magnet. Isn't it? I'm making a demonstration so that you can understand. Here is the coin. The coin is parallel to the magnetic field line. Can you see? Here are the magnetic field line. This is a coin. It is facing in this direction. It is parallel to the magnetic field line. Then let us focus. What is angle theta? Remember I said for current we use cos. Current we use cos. So since we are plotting a graph of current V versus time, current time graph. So the position of the coin is parallel to the magnetic field line. So theta, what is theta? It means theta is going to give us 90 degrees. Theta is going to give us 90 degrees. When we get this 90, I told you that the normal line in the coin, it is positioned in such that when the coin is parallel to the magnetic field, then the normal line is perpendicular to the magnetic field, as I demonstrated through this black line. This coin is parallel to the magnetic field line. What is happening to the normal line? The normal line in the coin. The normal line is perpendicular. When the coin is parallel to the magnetic field, the normal line is perpendicular. When the coin is perpendicular to the magnetic field, the normal line is parallel. Do you understand? That's where you get that. So I've positioned it here. I want to draw starting from here. Can you see? I'm starting from here. What will happen? So what will happen here is that since I'm starting in this position, the coin is parallel to the magnetic field. The normal line is where? The normal line is perpendicular to the magnetic field. So it means here we're going to have cos 90. Cos 90 is equals to 0. Meaning that cos 90 will make everything 0. It means at that position, what is happening? We're going to have 0 current. At the position where the loop or the coil is parallel to the magnetic field, we're going to have a 0 current. There will be no current which is being induced, and there will be no voltage which will be induced. Yes, we're going to have nothing at this point. We have no current. Let me not talk about voltage. Let me focus on the current so that I avoid confusing you. So you see, it means we're going to have what? We're going to have a zero current. You see? I will plot. I will show you what will happen. It means my graph is going to start from 0. Why is it starting from 0? It's because of the position of the what? The position of the coil. The coil is parallel to the magnetic field. What about the normal line? Normal line is perpendicular to the magnetic field. Here's the normal line. And the theta is the angle between the normal line and the magnetic field. So it means that angle between this line and these lines of magnetic field is 0. Normal line is perpendicular, meaning the angle between these two, it will be 90. You understand? So since the angle between the normal line and the magnetic field is 90, we're going to have a 0. Everything will become 0, so we'll have 0 there. So look what will happen next. Look what will happen next. Then the coil turn. When the coil turn, it becomes like this. Look at what we have now. Now the coil is perpendicular to the magnetic field. Do you see? The coil is perpendicular to the magnetic field. What about this black line which I said it is the normal? I'm just demonstrating a normal. It means now the normal is parallel to the what? To the magnetic field. And when the normal line is parallel to the magnetic field, it means angle theta is equal to 0 degrees. Why is it 0? Because there is no angle between these two lines. It's like the normal line is here. So there's no angle. The angle that is there is 0. And what does cos 0 give us? Cos 0 will give us a 1. Cos 0 will give us a 1. It means that we are going to get the maximum amount of the magnetic flux. If here we have got the, let's say we have numbers, we have got the 80 multiplied by 20, and it will become cos 1, meaning that we're going to get the product of 80 and 20. Can you see that? It's because now the coil have turned and it became perpendicular to the magnetic field. What about the normal line? The normal line is what? Parallel to the magnetic field, meaning that the angle between the normal line and the magnetic field now is 0, meaning that this graph is going to what? To go to the maximum. I hope you understand now. This graph will go to the maximum. Why is it going to the maximum? Because we get cos 0, and cos 0 means we multiply the magnetic field strength and the area multiplied by 1 to give us the maximum value. At first, why did this start from 0? It's because our theta was 90 degrees. Why 90 degrees? It's because the coil itself was parallel to the magnetic field, and when the coil is parallel to the magnetic field, the normal line of the coil is perpendicular to the magnetic field, which will give us 90, and cos 90 is 0. That's why it started from 90. I hope you can see now. Then it came here where the normal line became what? The normal line became 0. The angle between the normal line and the magnetic field, it became 0, which is something that we represented. Then we do what? In 10, what happens? Look at the third 10. The coil, what happened to the coil? In this direction, this time around, in an opposite direction, the coil, it has returned to be what? To be parallel to the magnetic field line. The coil has just become parallel to the magnetic field line again. What about the normal line? The normal line is now perpendicular to the magnetic field. This black line, I just drew it to represent for you to understand. So it means that we will have cos 90 again. Do you see? We have cos 90 again. Cos 90 will give us what? A 0, meaning that the current is going to come back to what? To 0 because we get cos 0. You understand? Now, it is like this. Can you see? Then, what will happen? It turned again. When it turned from its initial position was like this, and the angle between the normal line and the magnetic field is 0. Then it became like this. The coil became perpendicular to the magnetic field line. Then the normal line of the coil becomes parallel to the magnetic field of the line, giving us an angle between magnetic field line and the normal line 0. It turned like this. It went back to 90 degrees, I mean the angle. 90 degrees, the angle. Then, this time around, you see it have changed the phase. It have changed the phase. It's like, when it was turning, at first, it was, what is this direction? It was perpendicular like this. It is facing me, right? Let me just give you an example so that you understand. This thing is facing me. It turned. It is what? It is perpendicular. It is perpendicular, but it is no longer facing me. It is facing me. This thing, this side is facing me. It turned. It is perpendicular, but it is no longer facing me. The face is that side this time around, meaning that it has turned 180. When it is like this, it is at 0. It turned like this, it turned like this, it becomes 180 because it is no longer facing me. I think that's the best explanation that I can explain. It is like the window. When you look at the window from this side, then, and that side, that other side is 180 degrees from you. This other side is 0 degrees from you. I think that's the best way I can explain. When I'm looking at this thing, it is in phase with me. When it turns like this, it is perpendicular, but the face, it is that side. It means it has turned 180 degrees. So it means that initially it was like this. As you can see, it was like this. When it becomes 0, the angle is 0, it turns like this. Normal line is parallel to the magnetic field. It became, the angle became cos 0, then cos 0 is 1. This time around, the normal line is perpendicular to the magnetic field line. It becomes 90. That's why it will return back to 0. Then this time around, the normal line becomes what? Becomes parallel to the magnetic field line again. But this time is in opposite direction. It is negative, meaning that we're going to have cos. We're going to have cos what? Cos 180, cos 180, which will give us cos 180, which will give us negative 1. And negative 1, it means it will alternate and goes down. It has alternated and went down. The answer is negative. That's why it is coming back to the negative. Then, since it is in the negative, what will happen again? It turns like this. You see, you will see it will return to my face. We will face each other again. Then when it turns like this again, it becomes what? 0, because the normal line is perpendicular to the magnetic field line. Then it goes up again. When it goes up, what will happen? It goes up, right? Then it faces me again the way it was originally. So then we can represent that by going up again and again. So this is a full turn. This represents a full turn. If you notice, you will see that I've turned this thing 4 times. The 5th time it returned to its position. Remember, it was like this. That's why the current is 0. Why is the current 0? It is because the normal line is perpendicular to the magnetic field line. The normal line is perpendicular to the magnetic field line. So when the normal line is perpendicular to the magnetic field line, it means the angle between the magnetic field line and the normal line is what? Is 90, and cos 90 will give us what? Will give us a 0. That's why there is 0 current. So it means when the coil is at this position, it is not producing any current. Then it turns. Remember the magnetic field line here. The magnetic field line, this is the north pole of the magnet, this is the south pole. So what will happen? The first time, 0. For the first time, it turned like this, it became, the normal line, this black color became parallel to the magnetic field, giving us the angle between the normal line and the magnetic field line to become 0. Cos 0 give us a 1, meaning it will give us a maximum number. If here we have got the 80 and the 20, for example, or we've got the 10 and the 4, that maximum number, it means it won't be cancelled. We'll just multiply it by 1. And when you multiply something by 1, you didn't change, meaning you get the maximum number. That's why here the current went up. It means current went up. Then when it turned again, what is happening between the normal line and the magnetic field line? The angle between them is 90. Cos 90, 0. That's why it went to 0. It turned again, but this time the face is in the opposite direction. I was looking at this face initially. This time I'm looking at this other side of the coil. Meaning that it have turned how much? It have turned 108. It have turned 108. Then when it have turned 180 degrees, what will happen? It means that the angle between the normal line and the magnetic field line is 108. This is the normal line. Cos 108 will give us -1. It means we're going to get the maximum value, but the maximum value will be negative. That's why it goes down. Then it return to the original position. Then the original position, the normal line is perpendicular to the magnetic field line. Then the theta is 90, then cos 90, it returns back to 0. So I hope you have understood how the graph for current work. We can do a recap. For current, we use cos. For current, we use cos, whether it's in the AC or a DC. For current, we use cos. I want to explain the DC current now. After doing this recap.